Hello, welcome back, everyone. We are in the second of three lectures on Chapter 9 in Fundamentals of Inorganic Glasses. Chapter 9 is all about the viscosity of glass-forming liquids. Last time we covered what is viscosity. We covered various ways of measuring viscosity and the fact that viscosity varies by many orders of magnitude with respect to temperature. Today, what we're going to do is focus on different models to describe the temperature dependence of liquidus viscosity. Let's begin with one of the most important plots from the previous lecture, which is this angel diagram introduced by Professor C. Austin Angel from Arizona State University. And if you recall, what Angel did was he took the viscosity versus temperature curves for a wide variety of different glass-forming chemistries, from silica and germania through chalcogenide systems like arsenic sulfide, ionic liquids like zinc chloride, organic liquids like toluene and orthoterphenol, and he put them on these normalized temperature axis here, where this is a normalized inverse temperature. It is 1 over the temperature divided by 1 over the glass transition temperature, which gives us Tg over T. And then the y-axis is the base 10 logarithm of viscosity. Remember that those units are expressed as poise on the left axis and Pascal seconds on the right axis. Since there is a factor of 10 difference between poise and Pascal seconds and a logarithmic set of axes, the difference is just 1 unit. Now, all of the curves pass through this common point here at Tg over T equals 1. This is the glass transition temperature, where the viscosity is 10 to the 12 Pascal seconds or 10 to the 13 poise. This is Angel's definition of the glass transition temperature. So for any composition X, the glass transition temperature is defined as being that temperature at which the viscosity of the liquid is 10 to the 12 Pascal seconds. So all of these curves converge on that point by definition. Now, if we look at the other side of the plot here at Tg over T equals 0, this is the limit of infinite temperature. Obviously, there's no directly measured data there, so this is determined by extrapolation. And what Angel did was he fit all of these measured viscosity data for all these different liquids and extrapolated the model fits to infinite temperature and saw that they also passed through a common point, this universal upper temperature limit of the viscosity. And then Angel found that the liquids can be classified into 2 different types of scaling. A couple of the liquids, silica and germania, exhibited this straight line scaling of the logarithm of viscosity versus Tg over T. This means that the viscosity scales erroneously for those liquids, and he classified them as strong liquids, supposing that their structure did not change very much as a function of temperature. Then all of the other liquids exhibited some departure from Arrhenius scaling. They have these curved lines here, and these he called fragile liquids, indicating that since the slope of the viscosity curve was changing with temperature, that means the activation barrier for viscous flow was changing with temperature, and therefore the structure of the glass-forming liquid is probably also changing. So we had this classification of strong liquids and fragile liquids. And then the next thing Angel did was to quantify the fragility via this fragility index, which is the lowercase m. And the fragility index is defined as being the derivative of this base 10 logarithm of viscosity versus Tg over T curve evaluated at the glass transition temperature of T equals Tg. So it is the slope of this curve right here, where a greater fragility index indicates a steeper slope and therefore a greater departure from Arrhenius scaling, therefore a higher fragility. So the lower limit of fragility according to this diagram would be 12 minus a minus 5. So the lower limit would be 17, which is approximately what it is for silica and germania. And then as the slope becomes steeper, indicates a higher value of fragility. So what this means is that there's 2 key parameters that govern the composition dependence of viscosity curve, the glass transition temperature, and the fragility index. Now, implicit in this is a functional form that Angel used to do the fitting of the experimental viscosity data to some equation. And the equation that Angel used is this Vogel-Fulcher-Tammann, or VFT equation, which is an empirical equation that describes the temperature dependence of viscosity. And this dates back to the 1920s. It was actually proposed independently by three different authors, by Vogel, Fulcher, and Tammann. And the paper that has kind of the greatest elaboration on the model itself and validating the model is the one by Gordon Fulcher, published in Journal of the American Ceramic Society back in 1925. And the Fulcher equation, or this Vogel-Fulcher-Tammann equation, VFT equation, is given here in the middle. The base 10 logarithm of viscosity is equal to some constant plus another constant divided by temperature minus a third constant. So there are three independent parameters here. And this is basically a variation on the Arrhenius equation, where if this T0 is equal to 0, then the second term in the equation is just a constant over temperature. Since this is the logarithm, that means that this would just be an Arrhenius equation. It becomes non-Arrhenius by taking that T and changing it to T minus T0. So any non-zero value of T0 indicates that there's going to be some degree of fragility to the system. So Fulcher and Vogel and Tammann all settled on this equation as being a good empirical equation that had just a few parameters, three parameters, and could give a fairly accurate representation of the temperature dependence of viscosity. An example of that is shown here. So this is the base 10 logarithm of viscosity versus temperature. The raw data for a glass-forming borate liquid, B2O3 liquid, are shown as the open points. And then the fitted curve here to the VFT equation is shown by the dashed line. And it gives a pretty good representation. However, if you zoom in at the low temperature end, what you can see is that there's some systematic error there in the VFT equation, where the VFT equation is steeper than the experimental data. And if you look at the functional form of the VFT equation, it should be pretty clear why that's the case, because if this temperature T in the denominator is approaching T0, as T becomes equal to T0, then you've got 0 in the denominator, which would cause the viscosity to become infinite, which is an unphysical result. The reality is that viscosity can only become truly infinite when the temperature approaches absolute zero temperature, because only in that limit do you have zero thermal energy and therefore have a genuinely zero probability of undergoing viscous flow. So there is kind of a mathematical artifact here in the VFT equation that does lead to this type of systematic error at low temperatures. Several models have been proposed to try to correct that error. One of the more successful ones is this Avramov-Milchev equation, or AM equation, where the logarithm of viscosity is equal to some constant here, plus a constant tau over temperature raised to some power alpha. So the number of parameters here is the same, 1, 2, 3 free parameters, the same as the VFT equation. It is able to capture the non-Arrhenius scaling of viscosity by having any value of alpha that is not equal to 1. And it provides an improved fit of the of actual measured viscosity data. And the nice thing about the Avramov-Milchev equation is that it only diverges in the limit of temperature going to absolute zero, meaning that the viscosity of the AM equation only approaches infinity in the limit of zero temperature, which is a physically realistic extrapolation. So the Avramov-Milchev equation is certainly an improvement over the Vogel-Fulcher-Tammann equation. Another equation that has a greater physical basis that I want to dive into in a bit more detail is the Adam-Gibbs equation for viscosity. This is the so-called entropy model of viscosity. And what Adam and Gibbs did was they derived an equation that represents either the relaxation time of a supercooled liquid or its viscosity, so a kinetic property. They relate that kinetic property, the viscosity, to a thermodynamic property, which is the configurational entropy of the supercooled liquid. I'll show you some of the steps of the derivation in a moment, but for now I want to paint the physical picture behind the Adam-Gibbs model. So what Adam-Gibbs assumed was that any liquid that exhibits viscous flow would consist of a number of regions within that liquid that can cooperatively rearrange. So viscous flow is not just single atoms or molecules flowing on their own. Viscous flow is a cooperative flow of a whole region of atoms that need to flow together. Each region is composed of a group of Z number of atoms or molecules, and those Z number of atoms or molecules can rearrange themselves independently of its environment. So they cooperatively rearrange with each other, but they do so independently of the atoms outside of that region. Now, as the liquid is supercooled, the size of these cooperatively rearranging regions grows progressively larger. In other words, as the system cools and the viscosity increases, that means the fluidity of the system is going down, the size of these cooperatively rearranging regions becomes larger and larger because it requires greater cooperativity among the motion of these atoms. Now, since the size of the regions becomes larger, this yields a decrease in the configurational entropy of the system, and that causes an increase in the viscosity of the liquid. And this process continues until the configurational entropy becomes zero in the limit of zero temperature, at which point the viscosity becomes infinite. So that's the picture. The picture is that a liquid exists of cooperatively rearranging regions. They need to flow together in order to have viscous flow. As the liquid is cooled, the size of these cooperatively rearranging regions becomes larger. That yields a decrease in the configurational entropy of the liquid, which in turn gives a higher viscosity. What does this look from a mathematical point of view? The key steps of the Adam-Gibbs derivation are shown here, where what they did was they started with the partition function in the isothermal isobaric ensemble, so looking at constant pressure. The partition function here from statistical mechanics would be summing up over all the Boltzmann probabilities for every number of different states that you can have here. W is the degeneracy of the states that satisfy having region size Z, energy E, and volume V. That's the number part. And then times the Boltzmann probability factor e to the minus enthalpy over kT. That e to the minus enthalpy over kT can be divided into e to the minus internal energy over kT, and then the pressure times volume part of the enthalpy. Now, from this isothermal isobaric ensemble, we can get the Gibbs free energy of the system by taking minus Boltzmann's constant times temperature times the natural log of the partition function. So far, so good. Now, Adam and Gibbs are going to make an assumption. They're going to assume that out of all of these different microstates, there is only a restricted set of those microstates that would allow for viscous flow or allow for a transition. And they called this a restricted set, and they calculated a restricted partition function, which is delta prime, where the summation in that case is only over the states that allow for viscous flow and not over the other ones. And in that case, one can define a restricted Gibbs free energy G prime based on minus kT times the natural logarithm of that restricted partition function. So we've got a Gibbs free energy of the entire system, and then a restricted Gibbs free energy just for the subset of systems that allow for a viscous flow. The fraction of systems that allow for viscous flow is given by this little f, and that is just the ratio of the two partition functions. So the partition function of systems allowing for flow over the total partition function. And using that relationship between the partition function and the Gibbs free energy, this just becomes exponential of minus difference of Gibbs free energy between those two cases, between the restricted case and the full system over kT, Boltzmann's constant times temperature. And then this difference of the Gibbs free energy here, this can be expressed in terms of the chemical potential difference between those two states. The chemical potential difference here is delta mu, and then the size of the region here is Z. And what this means then is that the probability of being able to make a transition, or the probability of being able to have viscous flow, is proportional to F, the fraction of systems that allow for rearrangement. This probability, P, is a function of temperature, T, and is equal to some constant here, A, times exponential of minus size, Z, times the chemical potential difference, delta mu, over kT. Now, the next thing that Adam-Gibbs did was to assume that there is a minimum size region that allows for cooperative rearrangements, and that minimum size increases as the temperature of the system is lowered. So there has to be at least Z star number of atoms or molecules in a region in order to allow for viscous flow. So then in calculating this average transition probability, the lower limit of the summation starts at Z equals Z star, which is the size of the smallest cooperative rearrangement, cooperative region with a non-zero transition probability, Z star. And then they sum up to infinity. And you'll note that Z here goes in the argument of the exponential, e to the minus Z delta mu over kT. The next assumption that they make is that out of this entire summation, the term that matters the most is the smallest Z, because any larger Z's would make this exponential decay term become much larger. And so they just pick off the one term that matters the most, which is the Z equals Z star term. And that is what gives this equation here, which says that the average transition probability is equal to some average value of this prefactor A times e to the minus Z star times delta mu, the chemical potential difference, divided by the thermal energy kT. The next step in the Adam-Gibbs derivation is to relate this to the configurational entropy of the system. According to Boltzmann's equation for the configurational entropy, S config must be equal to Boltzmann's constant K times the natural logarithm of the number of possible microstates that satisfy whatever the macrostate is. Following the assumptions in the Adam-Gibbs model, they're assuming that each cooperatively rearranging region is able to flow independently of the other cooperatively rearranging regions, and therefore the total system here can be written as a summation of each of the subsystems, where each subsystem is the cooperatively rearranging region. If the configurational entropy of a single cooperatively rearranging region is the little s config, then we multiply that by the number of regions, little n, which is related to Avogadro's number, or whatever the size of the system is, divided by Z, the number of atoms in a particular region. So this is what gives us the overall configurational entropy of the system. And if we relate this to this key minimal size here, Z star, what this means is that the Z star, the size of this minimally sized region that allows for rearrangement, is equal to the S config star, so the configurational entropy of that sized region, divided by the total configurational entropy of the system times then the number of atoms in the system. So on the order of Avogadro's number here, Na. So this is relating Z star to S config star and the configurational entropy of the entire system. This all gets put back into this exponential here, that expression for Z star. And when we do that, then the average transition probability is equal to some prefactor here, A, times e to the minus configurational entropy of that minimally sized region, S star config, times Avogadro's number, or whatever the size of the system is, times the chemical potential difference over KT S config for the entire system. And what we can do is take all of the constants and unknown things and lump them together into an unknown constant. So this unknown constant C is just equal to the S star config times Avogadro's number times the chemical potential difference divided by Boltzmann's constant. And that's what gives us the equation here. And then the net result is that the molecular relaxation time tau, or the viscosity eta, is proportional to E to the some constant here, C, over temperature times the configurational entropy of the system. So that's the key result, the key equation from the Adam-Gibbs model. And the cool thing about this is that it's relating a kinetic property, namely the molecular relaxation time, or the viscosity, to a thermodynamic property, which is the configurational entropy of the liquid. Now, if we relate this back to Angel's classification of strong and fragile liquids, what this means is that if the configurational entropy is a constant, then the viscosity would scale Arrheniusly. And so a strong liquid having an Arrhenius viscosity curve, would have a constant configurational entropy with respect to temperature. While if you had a configurational entropy that varies with temperature, then that would lead to non-Arrhenius scaling from this formula. So what Adam-Gibbs are doing is saying that the physical origin of whether a liquid is strong or fragile relates back to whether or not the configurational entropy varies with temperature for these systems. Now, there are a couple of shortcomings of the Adam-Gibbs model. First of all, it does not provide a means of calculating the size of the cooperatively rearranging regions or this unknown constant C. And also, if you go into the non-equilibrium glassy state, it doesn't account for the thermal history effects of the viscosity. So picking up from there, that was kind of the state of the art when I started working in this area. One of my colleagues at Corning wanted me to look into this problem to see which of the published viscosity equations was the most accurate, because we wanted to use the most accurate model as possible, which is some very practical motivation here. And also, would we be able to predict low temperature viscosity behavior based only on the easier high temperature viscosity measurements? So there's some very practical motivations here for trying to find out what is the best description of the viscosity temperature dependence. There's also some really interesting underlying physics questions here, such as, is there a universal scaling of the viscosity versus temperature for all liquids? In other words, can we use the same equation to describe the viscosity temperature dependence for all liquids? With the VFT equation, is there any evidence that a viscosity would actually diverge at some finite temperature below the glass transition temperature? Believe it or not, this actually had been debated in the literature for many decades, even though I'd argue that it's quite obviously unphysical to have an infinite viscosity at a non-zero temperature, because even if there's a small probability of making a transition, a small probability is still not an infinite viscosity. It only becomes infinite, of course, in the limit of absolute zero temperature. And there had been a lot of speculation in the literature also that this divergence of viscosity predicted by the VFT equation at T0 would somehow correspond to some type of thermodynamic singularity. And there had been a lot of speculation about that as well. So what we did was to come up with our own equation to describe the temperature dependence of viscosity. It is this MYEGA equation. And we started with the Adam-Gibbs equation because that had a pretty strong physical underpinning. And we can write the Adam-Gibbs equation as the logarithm of viscosity is equal to some constant here, which is the logarithm of the infinite temperature viscosity. Because note if the temperature goes to infinity, then what's left is this eta infinity here, the infinite temperature viscosity. So it's that term plus, since we're in logarithmic units here, the exponential goes away and it's just plus some unknown constant, which I'm labeling here as B, which is a function of composition, divided by the temperature times the configurational entropy of the liquid, which is a function of temperature T and composition X. Now, the next thing we did was to make use of an expression from Gerardo-Naumus, which relates the configurational entropy of a system, specifically of a liquid system or a glassy system, to its number of topological degrees of freedom. If you remember back to our lecture on topological constraint theory, a floppy mode in a system allows the atoms to be able to move in a cooperative fashion with very little or no cost in energy. And what Naumus showed was that the configurational entropy of a liquid is proportional or largely proportional to the number of these floppy degrees of freedom based on this topological description of the glass network. And so with that proportionality, then the next thing we can do is assume that there is a simple two-state system here between a system that is fully rigid in the limit of zero temperature, and then a system that is fully floppy in the limit of infinite temperature. And what that means is that as the temperature goes to infinity here, this exponential term would go away and it would become 1. And then the number of degrees of freedom per atom would be 3. Those are the 3 translational degrees of freedom in the X, Y, and Z directions. And then those degrees of freedom disappear in the limit of low temperature as all of the bonds become rigid and the floppy modes disappear. So what we do is we take this expression for the degrees of freedom, stick it into the expression for the configurational entropy, and then back into the Adam-Gibbs equation, collect all the unknowns together, and what we have is a new functional form for the temperature dependence of viscosity, which is the MYEGA equation published here in Proceedings of the National Academy of Sciences in 2009. The equation here, the MYEGA equation, is that the log of the viscosity is equal to the log of the infinite temperature viscosity plus some constant K over the temperature times E to the some other constant C over temperature. So it's the same number of constants as both the VFT equation and the Avramov-Milchev equation. We've got 1, 2, 3 unknown quantities. Like the Avramov-Milchev equation, the viscosity only diverges in the limit of absolute zero temperature. So as the temperature goes to 0 K, 0 Kelvin, then and only then does the viscosity diverge towards infinity. So this satisfies that criterion. And what we want to do now is to put all of these on kind of an even playing ground and see some of the intrinsic differences in shapes predicted by these 3 viscosity models, the VFT model, the Avramov-Milchev model, and the MYEGA model. And all of them already had one of the parameters in common, which was the infinite temperature viscosity eta infinity. That's the same first term here. But the other 2 parameters were all had different physical meanings in the 3 different equations. So what we can do is use Angel's definitions of the glass transition temperature Tg and the fragility index M, and then rewrite each of those 3 expressions in terms of a common set of variables. So these are all now written in terms of eta infinity, glass transition temperature Tg, and the fragility index M. The equations that I'm showing here are all mathematically equivalent to the equations that I showed previously for each of these models. It's just making a change of variables to get them all described in terms of the same parameters. And when we do that, we can see some of these intrinsic differences in shape. So this shows the angel diagram here in this box that goes up to the dashed line of 12, and from Tg over T equals 0 to Tg over T equals 1. So everything inside this dashed box is the angel diagram, but then we extrapolate this to even lower temperatures to see some of the differences in the shapes of these models at low temperatures. From Angel's definition of the glass transition temperature, we know that at Tg over T, the viscosity goes through 10 to the 12 Pascal seconds here, so this intersection point. We also assign the models all the same values for A to infinity, for Tg, and for M. So they all have the same parameter values, and that allows us to see some of the differences in shapes among these different models. So this is assuming 10 to the minus 4 for the A to infinity, and then assuming the same value of Tg and the same value of the fragility index. So it's the same slope of the viscosity curve at the Tg. And now we see these differences in the scaling behavior among the three models. The VFT equation, even though it has the same slope here, actually comes in with the greatest amount of curvature. And it has the greatest amount of curvature because it is trying to shoot up to infinity at some finite temperature. So it is diverging at some finite temperature, and that's what's giving it the greatest amount of curvature. The least amount of curvature actually comes from the Avramov-Milchev equation in red, and the MYEGA model falls somewhere in between the two and a little bit closer to the Avramov-Milchev equation. Now, what does this imply in terms of the scaling of configurational entropy in the system? If we assume the Adam-Gibbs equation to be valid, we can solve for the what is assumed for the temperature dependence of the configurational entropy in each of the three viscosity models. And the two plots shown here have the configurational entropy on the top as a function of inverse temperature. And then at the bottom, we flip the x-axis, so it becomes a function of temperature. So starting at the bottom, what we see is that the VFT equation actually comes down and predicts a divergence of viscosity, so infinite viscosity at finite temperature. According to the Adam-Gibbs model, that infinite viscosity would only correspond to a configurational entropy of 0. So the VFT equation is predicting a crash, a complete disappearance of configurational entropy at some finite temperature, while the other two models here, the Avramov-Milchev and MYEGA models, are showing a continuous loss here in entropy. And even though the entropy becomes very small at low temperatures, it only gets to 0 configurational entropy in the limit of absolute 0 temperature. So it's a smooth decay, which is much more physically realistic. Now, this kind of loss of configurational entropy in the VFT case has led people to speculate that there might be some what's called an ideal glass transition there, or some sort of entropy paradox called the Kaufman paradox. And there has been a lot of literature kind of speculating on that topic, whether something like that exists. Of course, this is not physically realistic because, consistent with the third law of thermodynamics, the entropy can only go to 0 in the limit of absolute 0 temperature, because then and only then are flow processes completely forbidden. So this behavior in the VFT equation is unrealistic, whereas the scaling behavior of the Avramov-Milchev and MYEGA equations is physically realistic. Now, if you flip the x-axis and go up here, now it's Tg over T. Now going to 0 on this Tg over T plot implies the limit of infinite temperature. And what we see is that the VFT equation and MYEGA equations both show a convergence of the configurational entropy in the high temperature limit, because even if, at the limit of infinite temperature, all of the configurations in a system are equally accessible, but the number of those configurations is still finite. It's not an infinite number. And therefore, the convergence of entropy in the high temperature limit is physically realistic. However, what Avramov-Milchev assumes is that the entropy diverges in the limit of infinite temperature, which is physically unrealistic. And that's why the Avramov-Milchev equation has the shallowest viscosity curve. The VFT equation has the viscosity curve with the greatest curvature, and the MYEGA equation is falling somewhere in between. This becomes a bit of a Goldilocks problem where what we know is that if you can get physically reasonable limits in both the limit of infinite temperature and the limit of zero temperature, all in the same model, that model has a much greater chance of being able to accurately characterize all of the points in between. So out of the three models here, the MYEGA model gets it correct in both the infinite temperature and the zero temperature limit. The Avramov-Milchev equation does the low temperature end well, but not the high temperature end. The VFT equation is the opposite. It does the high temperature end well, but not the low temperature end. And so let's try it out. Let's try out the MYEGA model on a bunch of different systems. You can see that the model fits here in the curved lines. Show very good agreement with the experimental data for a wide variety of different systems here, covering a wide range of fragilities from a very strong system like silica to very fragile systems like some of these ionic and organic glass-forming liquids. But let's really put it to the test here by doing extrapolation. Part of the motivation for doing this was to see, would we be able to predict the low temperature viscosity scaling, so these high values of viscosity based only on high temperature or low viscosity measurements. So what we have here is an example of a measured log viscosity versus temperature data. The measured points are shown as the solid diamonds, and it's just measured at the high temperature end here. The highest temperature cluster here was measured using the rotational viscometry method. And this point here at the softening point of 10 to the 6.6 Pascal seconds, that was measured using the parallel plate method. So these are all accurate viscosity measurements. What we do is we independently fit these data to each of the three models that we had discussed, the VFT model, the Avramov-Milchev equation, and the MYEGA model, and then extrapolate the models to low temperature and see at what temperature do they predict the 10 to the 11 Pascal second isocon. At what temperature do they predict that it would have this constant viscosity of 10 to the 11 Pascal seconds, and then compare that to the actual measured data from beam bending viscometry and see which of these extrapolations was the best. And what you can see is that the error in that isocon prediction is the greatest for the VFT model. And in fact, the average error for VFT was about 9.5 Kelvin. So it is over predicting the low temperature viscosity isocon by 9.4 Kelvin, which is actually a pretty significant error. And that is because it is trying to get to infinite viscosity at finite temperature. The Avramov-Milchev equation does the low temperature end well, but not the high temperature end. And as a result, it's tilted in the opposite direction. It does do better overall compared to VFT. The average error is minus 5.6 Kelvin, so it's certainly better than 9.4, but it's systematic error in the opposite direction because it is too shallow. The MYEGA equation, because it gets both the limiting behaviors and both the high and low temperature limits properly, is able to do that extrapolation without any systematic error. And the measurement error here is plus or minus 1 Kelvin, and the MYEGA equation gets within half a Kelvin. So it eliminates that systematic error. This raises the question of why the VFT equation does perform so well at high temperatures. And one of the interesting things you could do is actually derive the VFT equation from the MYEGA equation in that limit of high temperature. And this is interesting because the VFT equation is not derived in itself. It is just an empirical equation. But if we start with the MYEGA equation here on the upper left, and if we put this exponential into the denominator, it picks up a minus sign there in the argument. If we have the limit of high temperature, so a large value of t, that means the argument of this exponential becomes small, so we can do a Taylor series expansion of the exponential. And if we just keep the linear term there, that Taylor series expansion of the exponential is 1 minus k over t. Now multiplying this t through here, what we get is this function that says that the viscosity is approximately equal to log of the infinite temperature viscosity plus c over t minus k. So this is exactly the same functional form as the VFT equation, where the T0 from VFT is now approximately equal to the k from the MYEGA equation. So this is why the VFT equation works well in the high temperature limit. It's actually a pretty good approximation of the MYEGA equation and can be derived from the MYEGA equation using a Taylor series expansion of the exponential. As the temperature of the system is lowered, this Taylor series approximation becomes worse and worse and worse. The lower you go in temperature, the worse it becomes, and that's why the VFT fails at the low temperature limit. Another interesting question is about the universality of this high temperature limit of viscosity eta infinity. And what we did here was to test this out for 568 different compositions to see if indeed Angel's prediction of a universal infinite temperature viscosity eta infinity, if that is true. And what we found is that, yeah, there was a fairly narrow distribution of eta infinity values for each of the models, but the narrowest distribution was for the MYEGA model here shown in green. Because of the different curvatures of the model, the averages are shifted. From the MYEGA model, it seems like 10 to the minus 3 Pascal seconds is really a more accurate estimate for this infinite temperature viscosity compared to what Angel had obtained from the VFT equation. So the MYEGA equation gives a pretty narrow distribution of eta infinity values. And in fact, there was no evidence for any systematic variation of eta infinity with respect to composition. So the width here is basically just the noise of the fit. So this is a pretty good indication that Angel's assumption of a constant eta infinity is probably valid. And that is important because his definition of the fragility index depends on having that be a common point of intersection. As a last topic here in this lecture, I wanted to point out that even though most glass-forming liquids can have their viscosity described by a three-parameter viscosity model like BFT or Avramov-Milchev or MYEGA equation, there are a few systems, including the usual suspects here, water and silica, as well as some metallic glass-forming liquids, where a three-parameter viscosity model is not sufficient. And in fact, in these systems, they exhibit what's called a fragile to strong transition, where at the high temperature end, if you just look at the high temperature end, it's like this high temperature dashed line. It appears to be quite fragile, but at low temperature, it appears to be rather strong. And there's no way to use a single three-parameter viscosity model to fit both of these regimes. So what we did was to derive an extended MYEGA equation where instead of assuming a two-state system of rigid and floppy, we add a third well to that. And if a third well is added, then you've got an intermediate state in between the two. That actually gives two additional parameters. So now this has 1, 2, 3, 4, 5 parameters. And in fact, there are these two terms here on the denominator, two exponential terms, the two different weighting factors, and two constants in the arguments here. One of those terms would be the strong term. The other term would be the fragile term. And when you put them together, you get the red curve shown here. And you can see that this is connecting both the fragile region at high temperatures and the strong region at low temperatures, all with a single expression. So this is observed in a lot of metallic glass forming systems. So just keep that in mind. Our glass great for the day is Gordon Scott Fulcher, who lived from 1884 to 1971. He was born in Evanston, Illinois, the home of Northwestern University. He got his PhD in physics at Clark University in 1910, and he, during World War I, did naval research. He joined the research staff at Corning Glassworks in 1920, where he spent most of his career inventing and developing electrocast refractory materials. While he was doing that, he also introduced the Fulcher equation for viscosity, this VFT equation for viscosity. At the same time, he also served as the editor for Physical Review in 1923 to 1925. And while he did that, while he served as the editor of Physical Review, which is the most prestigious journals in physics, he instituted this modern system of abstracting. So he came up with the idea that scientific papers should be organized with abstracts and keywords, and he had a system to do that. And this system was adopted by the League of Nations, such that all scientific papers then had to adopt Fulcher's system for abstracting. He ultimately left Corning to become director of research at Core-Hart Refractories, which was a joint venture between Corning and Hartford Empire back in 1934. And he was also very interested in psychology and metacognition, the science of thinking. And he published two books in those areas called Better Thinking for Better Living in 1948 and Common Sense Decision Making in 1965. So I believe Fulcher represents a great argument for why it's so important for industry to collaborate closely with academia. He really built that strong bridge between industry and academia. So to summarize this lecture, the VFT equation was an empirical equation that had been the standard expression for viscosity for about 90 years. However, it suffers from the problem of divergence at finite temperature. The Adam-Gibbs model, or the entropy model of viscosity, proposes that liquids are made of cooperatively rearranging regions which increase in size as the liquid is cooled, lowering the configurational entropy of the system, which leads to higher viscosity. The MYEGA model is derived from the Adam-Gibbs model and provides a more kind of easy to implement approach for the viscosity versus temperature relationship. All right, that does it for this lecture. Next time we will finish up chapter 9. The third and final lecture in chapter 9 is on the composition dependence of viscosity. All right, thanks everyone. I'll see you then.